Conway's Game of Life is a very simple mesh program or mesh automata that just requires integer computations. And so we don't have to talk about the partial differential equation we're attempting to solve or whether the approximation is appropriate. So this is an exact implementation of this particular game. The nice thing about it is that it requires a stencil computation, just like a PDE solver. And it has these very simple rules. So you initialize a two-dimensional matrix with either live or dead, so there's one bit in each cell. And then at the end of an iteration, the next iteration of this matrix is live. The bit is set. If either the sum of the 8 neighbors is exactly 3, or the bit had been set, and the sum of the neighbors is either 2 or 3, and otherwise it goes to 0. So if you're too crowded or you're too lonely, you die. And if you have exactly the right number of neighbors, you can get born. Okay, and so on the right here is an example. There's an initial pattern. That's after applying the rule once, or 1 iteration, 2 iterations, 3 iterations, or 5 and 6. So in this case, everything died out. There are patterns that are stable, so there are patterns that live infinitely long. An interesting question that was posed was whether the population is bounded, and the answer is amazingly no. There are repeating patterns that can travel. They're called gliders. There are bigger ones called spaceships. And someone, I think it was at MIT, do you remember, Rusty? Someone came up with a bunch of dots that launches gliders, called a glider gun. The number of life forms in an infinite mesh goes to infinity as time goes to infinity. So to implement this, generally a good way to start is often to not think about parallelism to begin with, but think about how you would do it. Now, having said that, one caveat is that whatever you think about has got to be something that is amenable to appropriate parallelization. But in this case, we'll just sort of start, how would I do this? I have a 2D matrix, initialize the matrix, and each time step do that sort of computation. And so as we think about this, there will be a global array, which represents the data structure you would have in the absence of parallelism. And we'll decompose this, and we'll have our little pieces, which are called patches in this program. And there'll be a computation and communication on that local piece. So what you see, if, for example, if I start with a mesh like this, that's my real mesh. That's the way I want to think about the problem. We're not really talking about I/O, but when you do talk about I/O for things like this, particularly as you get to large numbers of processes, a natural way to describe the input and output is, let's not think about parallelism. I don't want to think about whether I ran that with 16,000 processes or 32,000 processes. I want to have output that is natural and independent of parallelism. So it would look, say, like that. And then this is my stencil. So this is a 5-point stencil. Conway's Game of Life has a 9-point stencil. So it's a little different, and that accounts for some of the interesting features of the code. So we do our decomposition. This is a decomposition into a 3x3 process grid. And so I've got my stencil there. That's fine. And if I look at it like this, but when I have, of course, I'm trying to compute life on this point, I need, well, for life, I need this one, and this one. And for that, we normally construct a halo around the data that we own. So the data that is my part, so if I'm this process, I own a part of the global grid. That's this piece here. And I have done this for 5-point stencil. So for the 9-point stencil, this whole edge here, the yellow part would be the halos. Once the halo is filled, I can apply the stencil to all of my interior points because I've got the data that I need there. So in the 5-point, I can just do this. So that's a put, if you want to use the RMA, or a send and a receive. So I took this edge, which is data that I own, and I sent it or put it to my up neighbor in the halo area. One interesting thing in the 9-point case, of course, this piece of data that I own is also needed over here. And so I could send it, and there's a version of the code that does that, but there's a trick called the diagonal trick. So the first step is I take this data and I move it over to these halo cells. Okay, and that's what you'll see in the code. And it does that, the basic version does that, even using an MPI vector data type. Now, what I do is I move not just this row that I own, but now the data here at the ends all the way up here. So that what that has done is it has taken this data here, moved it here, and then up here. So why would I do that? Well, that means that I've only had to do 4 sends and 4 receives to move data to 8 different places. I do have to synchronize twice as many times, but I have half as many overhead starts. And so depending on how efficient sends and receives are, this may be faster or slower, because there is a trade-off. The local data structure, so when I go through the description of the code, there's a number of structs. So in Fortran, that's what is that? That's a type with things in it. It has data about the decomposition of the processes into a mesh of processes and the global grid into these local patches. G is used to give the indices and sizes relative to the global mesh. So, and it's arranged as a matrix. So you start in the upper left corner, I goes down, J goes across. And so if I have a patch, my J is the first of the J index in the global mesh, and L in J is the local number in the J. So this would be global J plus that number minus 1. The program implements this. It has a bunch of files, so that it's easy to replace them, pick up pieces, and so forth. So first is, and of course, PowerPoint has auto-corrected the file names to make them incorrect. So that should have been there should be lowercase letters in some cases. So Mlife2d is the main program. It runs Life with 5 different choices for the exchange. The reason I'm doing that is to make it easy to do these timing comparisons and just look at those sorts of things. So it does 5 different choices of handle exchange implementations with 2 different communicators, and we'll see later why it's 2. It runs each of those twice. Why twice? Well, for some systems, the first time you run something, other stuff happens. You get initialization of the network. So if you're timing something and you don't at least look at and most likely throw away the first time that you execute a routine, you may not be timing what you think. You might be timing the time it takes to load a dynamic, a shared library into your node's memory. You might be timing the time it takes to establish a network connection to a destination process. And you may see that on some systems. So on the Cray system that I ran these on, the times for the first run and the second run were significantly different. I think on the Blue Jeans tends not to be. And that's just normal. If you don't effectively throw away the first time you run something when you're timing things, you need to stop doing that. And for each of those, it prints the time that it takes. So that's why you get so much output. Moptions.c contains the routines to parse the command line options. It uses a data type to distribute the options because one of the things that can be used is a string of characters, and so it's all sent in a single broadcast. Partly I did that to show you it really isn't that hard to create a struct data type and use it to do a single broadcast. And it returns those in a struct just to make it easier to pass a bunch of options back and forth. So for example, if you wanted to change the defaults, because the defaults are set up for something I'll show in a second, or add new options, that's the place to go. Patch.c does 2 things. It determines the decomposition of the processes into an array of processes, and determines the corresponding coordinates of my local patch for that global grid in that array of processes. And it returns that information in this patch description structure. And there's a couple of routines there because there's one that does the process decomposition sort of by hand, and another one that uses the MPI topology routines. And then a separate routine that does the assignment or the mapping of coordinates once you've got the process array, because that's the same in both of those cases. mtiming.c contains the guts, so since sort of the purpose of the program was to run some of these things and allow you to get times, but it, in fact, executes Conway's game of life. It's what, in fact, runs it. There's a loop over INJ that calls Mlife next step that implements the stencil computation for life. I'm very, very, very much aware that this is not the way one should write this for performance. It was written for clarity, but there's so many things that you could do to this to make it faster that I just don't want to get started, which is why I did it this way. For Fortran users, there's this sort of mysterious code that has parentheses star exchange, blah, blah, blah. That's simply calling a function that was passed as a parameter. And that function name would have been declared external in Fortran. And there's also a trick that's used to swap the pointers to the arrays so that I don't have to duplicate the code going from A to B and then from B to A, or from M1 to M2 back to M1. There are 5 files that implement 5 different ways to do the exchange. And the intent here is for you to add to this, so it makes it easy to compare different exchanges. And so there's this one in Mlife2d point-to-point.c that uses a vector data type and I sends and I receives, and it uses this diagonal trick. If you want to know whether that diagonal trick helps, there's a version that doesn't. There's a version that, instead of using the data types, just manually just has the code that you as a user might write to gather a strided vector into a buffer or unpack a buffer into a strided vector. And then there's also a version that sort of implements the example this morning where we use iReceives but sends. And finally, there's an RMA version using fence. Each of those files implements 3 functions. There's an init, an end, and an actual exchange. The init provides a way for you to pass data through to the actual exchange, for example, through a void pointer. If this is all mysterious here, just ignore it. Leave the 0 that's there in the example codes. And they all have different names. The functions are passed by name into the timing routine, again, to allow us to run many different types of exchange approaches inside the same program. There are a couple places where there's a mlife IO thing. I've included one file that implements a very simple character-oriented output to standard out. This is so you can watch the game of life as it executes. This one's set up only to do about 256 columns. It essentially assumes that you've got an X term and everything is visible. There's a init, a finalize again, and a checkpoint, which is used as an example for a bigger application where you might do checkpoints and restores. In our case, the checkpoint is show me the current state of the world. Show me what the current iteration looks like. Okay, so these lines are just telling you what you've run. So it's run a 1024 by 1024 global mesh. The process array is 64 by 64. So the 64 in the rows and 64 in the columns. And then here, rank 0 is giving you some data. If you look at the timing routine, it takes the max of the times. And these are little strings that go with each of this. So this is the point-to-point with the I receive, I send, wait all. This is the point-to-point with send, I receive. This is point-to-point with user handling of vectors, so no vector data type. This is the RMA with fence. This is the point-to-point not using the diagonal trick, so having the 8 I sends and 8 I receives. The time here is the per iteration cost of the entire loop, so that includes the computing part. This is the per iteration cost of the exchange part, the communication. And in the case where I'm packing and unpacking by hand, I can measure the cost of that time. So this is the amount of time it took me to pack, to gather that vector into a contiguous buffer, and to unpack the received contiguous buffer into the non-contiguous array. These times will tend to be, might be dominated by the cost of that inefficient computation. This is just the communication time. And one of the things we can see, let's see here. And then I have cart create and com world. So we've talked about doing this in com world, but I can ask for a communicator that is supposed to be a better fit for sort of nearest neighbor communication on a mesh, which I don't think we got. One of the things you can see, for example, is that on the machine in which this was run, RMA is not what you'd like to pick, because this is 2 times 10 to the minus 4 for the per iteration time. So at least it's about double at best the other times. The time to do the 8 sends instead of the 4 sends is noticeably higher than using the trick. So for this system, for this system at these sizes and so forth, using the trick was better. And sadly, data types are a performance penalty. That I'm seeing here is that my best choice tends to be user pack of data, and then the iSends, iReceives. Right, so that's what I'm seeing here. Well, note this was on Rajiv. This was on the which blue gene? This was on Vesta. Okay, so these you should be able to get data sort of like this, and we know that the data type performance on the blue genes is not what anybody would like. So just bear that in mind. This is not always the worst. This is not always this bad. When I take my global grid and then I drew lines through it, each little box there is a process is going to own that part of the mesh, and it's that mesh of processes that I'm talking about. And so in this case, it's 64 by 64. Now that you've seen that description, you can look at running it, for example, with somewhat bigger meshes. Also, the default is to just maybe be to do 1 iteration. If you do more iterations, you'll get more consistent, better time results. And so the -I gives you the number of iterations. If you're running it on your laptop with the default sizes, you could try running it with -C for checkpoint. If you do that, you will see that character formatted output that I talked about. And if you do it with like -C, -I10, each one of those tests will then show you the evolution of a random set of points. Note that the patch, I think it's the patch.c code has an initialization for the patch. It makes sure that independent of the number of processes, you get a random distribution that is the same on the global mesh. So that means that no matter what the process decomposition is, you should be seeing the same results. It allows you to check that. You can run that, observe what we just showed for fence, and then you can take the fence example, which has all of the grubby stuff needed to set up the windows, and you can just ignore that because you can just use it. Change it from using fence to using win, lock and unlock, and then see how that performs. So add that as a 6th exchange message into the Mlife2d main program, and then run the whole thing together.